Good morning, everybody. Got a lot of questions on the lab, how to fill out the table, how to work the lab, all sorts of stuff like that. So I figured today I'd kind of go over it with you a touch, and kind of give you. I don't want to give away the answers. I just want to give you something to help explain it a little better, and then we can talk answers at a later time. But I want to show you kind of how to work this thing first. If you didn't read the intro, I know it seems like a lot, but it's a good setup, and it kind of helps keep you in the mindset of what we're talking about with natural selection. But this table here is where we want to focus most of our energy in terms of this lab. So what we've got is two kind of options here. We can deal with mutations, and then we can deal with, it just says conditions, but it's environmental conditions. It won't let me click on it until I pick a mutation. So we want to make changes to either the animals or their environment that they live in, and then we want to see what happens based on those. So we're going to start with mutations. I would just go in order. It's easier, and that way you're not skipping around and forgetting where you were. So the first mutation that we're allowed to pick is large body, long legs. And these creatures are like rabbits. Although when you give them large body, long legs, they look kind of creepy. But anyway, you'll see in a second here. And then conditions, like I said, I would just go in order, but you can do new predator or restricted food. So we'll do large body, long legs, and then new predator. So we've got our rabbits, but then there's the mutant rabbit here who's got the large body, long legs. We're going to hit begin natural selection, and it's going to make some obnoxious noises and talk to you. So stay tuned for that.
5 generations later.
Thank you, random voice. So you saw the fox was going for one of the animals. If you noticed, he went for one of the normal animals. And look at what we're left with here. We've got 3 mutants now and only 1 normal. So without even looking at the data, that kind of gives us an indication of, is this mutation beneficial for these rabbit-like creatures? So let's go to the population graph, because here's where most of your data is going to come from. Now, if you get confused, it tells you up here, you're looking at the 1A population graph. So 1A, large body, new predator. Mutation is large body, conditions, new predator. And then we've got normal animals are the bluish, purplish bar, and then mutant animals are the orange bar. Now, look down here on the x-axis, we've got generation 0, 1, 2, 3, 4, 5, 0 being before we started the natural selection process, and then 5 being the end result. And then on the y-axis here, we've got number of animals living in this forest or wooded area, okay? So at our start, look at what we've got. We've got 50 normal, and we've got 10 mutants, okay? Now, this is 1A, so if I go to my graph and I go 1A normal, generation 0 was 50, mutant was 10, okay? Now we'll go back. And you don't have to do it this way. You can just do all the normal data first and then all the mutant data later, but I'm going to do it this way. Let's see. We're going to have to count those lines in between here. It looks like there's 1, 2, 3, 4, 5, 6, 7, 8. Looks like there's 10 lines. So each of these lines represents 1. So I'm going to say that is 40. It looks like 43. So we've got 43 for the normal under 1A in generation 1. And then we've got how many? Looks like it's 3 lines away from 20, so it's going to be 17 for the mutants. 17 under 1A mutant. Let's go to generation 2. Here we are. Looks like that is 30. And you can if you don't feel like staring at these little lines, they should have done a better job making it clear, but it looks like it is 1, 2, 3, 4, 5, 6. It looks like 7 to me. Actually, it looks like it's about 6. So we'll call that 36 for the generation 2 normals, 36. And then we're going to go to that looks like 21 to me. Yeah, we'll call it 21 for the mutants. Now you notice already we've got a trend developing. We don't even have to finish the data to really recognize this trend, although it's always a good idea to finish your data before you come to your conclusions. But look at what's happening. The normal population is decreasing every generation. The mutant population is increasing. Let's go to generation 3. I like when it's right on the line there. It's 30 for the normals. And then the mutants are, we'll call it 23-ish. Looks like 23. Generation 4 for the normals. We'll call that 21. And then generation 4 for the mutants. We'll call that 27. It looks like 27. And lastly, generation 5. Here we've got our normals look like they're at 19. And our mutants are going to be at, looks like that's 2 lines away from 40, so we'll call it 38. All right, so there's our trend. Now, I'm assuming, hint, hint, that the questions at the end of this lab are going to ask you about these patterns. And so when we think about this environmental condition and this mutation, we can tell that the mutants have the advantage here, right? Look at their population number. They are drastically increasing over generations compared to the normals that are, I don't know if I'd say drastically. They're losing about 7, 7, 6. Yeah, I mean, they're going down pretty significantly. So right away, without going further into the lab, we know that for these mutants, having a large body and long legs is an advantageous trait. Okay. And we remember from our discussion on natural selection that advantageous traits lead to greater reproductive success. Why do they lead to greater reproductive success? Because you're not being eaten. Okay. If you're being eaten by a predator, you cannot reproduce. So if you have an advantage, you're less likely to be killed. Therefore, you're more likely to be alive and reproduce and pass your genetics on. Okay. So that's just the first part. I don't know why it makes strange noises like that. Let's go to 2. Or I'm saying let's do 1B rather. Sorry. So large body, long legs, and then restricted food. So we've got 3 normals, 1 mutant. We see that
5 generations later.
We see the mutant just yeeted himself into the tree and started eating the berries. And then the normal, he tried to jump, but he was too weak and sad to be able to make it. So again, without even looking at the population data, now we've got 3 mutants, 1 normal. We can probably guess that this is also going to be advantageous. So let's pop it up here. So we're going to start with 50 and 10. We're at 1B now, okay? So we've got large body, long legs. B is restricted food. It's going to be 50 and 10 again to start with. I'm going to do it the other way now. I'm going to do all the normals first. So it's going to be 48 and then 41. This is probably the faster way to do it. And then it looks like it's 31, 2, 3, 33, 27, and then 18. So 33, 27, 18. So again, there's the pattern already. We are losing normals, and I'm going to go ahead and guess that we are gaining mutants. Look at that, the orange bars flying up. So we've got 12, 19, and then 26. 12, 19, 26. And then we've got 30, call it 34, and then 40. Notice I'm being a little bit more relaxed in how precise the numbers are. We see the trend, right? You don't have to zoom in and get the exact number right. I can see it's more or less 34 right here, right? Maybe it's 33, maybe it's 35. It doesn't look like 35, but again, you don't have to sit there and stare at the lines. I think it's poorly drawn. but get the trends right. That's what we care about. And again, we see the same pattern here. This mutation is beneficial. Okay. We're losing normals, we're gaining mutants over time. Therefore, we can conclude that the mutants are having greater reproductive success than the normals in this case. Okay. Now, don't think automatically that all of these mutations and all of these environmental conditions are going to be good. Okay. As you go further on, small body, white fur, let's say new predator, watch what happens here. And I'm not going to go through the data. I just want to show you this. Here's our mutant. And then we've got some normals out here. So let's say you are 5 generations later. Let's say you are the unlucky bunny that has white fur. That's your mutation. Look at what happens. There's no white bunnies left. Check their population graph, and they are getting wiped out. Now, interestingly enough, they bounce back a little bit right here, but then they are just getting smoked. They're almost gone entirely in that last generation, their generation 5. Now, you notice there's actually a pretty interesting trend for everybody. They're going up, and then they're going down, and then they're going back up. That's pretty regular for any population that's established in an area. You'll have times where your population will go up, and then it'll go down, and then it'll go back up. But in this case, the mutation does nothing good for this population. In fact, it's a huge disadvantage to have white fur in an area that's entirely green. Okay, not good. You don't want that. But then look at the next condition here. It's going to be snow cover. What do you think is going to happen? Obviously, the white fur mutant is going to have an advantage. So you're going to go through here, fill out the rest of this table in the way that we've been doing it, and then you can see the trends in your table, and then we'll go to the questions. So don't go to these questions, or I'm sorry, pause first. Don't let me answer the questions for you. I want you to answer them. Finish your table, answer them, and then come back to the video. So go ahead and pause me now, and then I'll go through the information here for these journal questions. So finish everything, and then come back, and then let's talk questions. So question 1 says, look at the information you recorded in your table for a particular mutation/condition. Describe how the population of animals change over time. I only filled out the first few, so I'm going to talk about 1A. And let me put this in red here so you can see it clearly. So it says, what's this question want? How did the population of animals change? How did they change over time? So let's talk about 1A mutants and 1A normal. So I'll talk about 1A. And let's see, that was large body, long legs, and new predator. So I'm going to establish what that was first. And now let's talk about what happened. Animals that did not have long legs / large body were caught and eaten by the new predator at a higher rate than those, those with the mutation. So we'll say, therefore, the mutant population increased and the normal population decreased. Let's check and make sure we answered that kind of fully here. It says, describe how the population of animals changed. Did I talk about populations? I did. So I explained kind of what was happening, and then I said, therefore, the mutant population increased. So I'd say that's question 1. That's a pretty good answer. If you have anything along those lines, you're good. Let's go to question 2 here. So referring to up here, I kind of already answered this a little bit, but I didn't give the details about reproductive success. So I want to make sure I include that here. So using your understanding of natural selection, explain why the population changed the way it did. In 1A, 1A, the mutation of large body / long legs allowed the mutants to escape the predator with greater success than the normal. Oops, there's two S's. And the normal. I don't want to call them bunnies because they weren't, but we'll call them bunnies. So we'll say therefore. I'm using therefore a lot today. Therefore, the mutants survived at a higher rate, which allowed them to do what? To reproduce more successfully over time. I won't say the mutants' DNA. Oh dear. Mutants' DNA becomes more. I'm going to use prevalent. You can use common. It would help if I spelled it right. Is that how you spell it? Sweet. Thanks, Google. So their DNA becomes more prevalent or more common or shows up more often because of their reproductive success. So there's kind of a lot to unpack there. Let me simplify that answer. I feel like it was a little bit wordy. Like I've been saying here, if you have an advantageous trait, if you have something that makes you good at surviving, you will live longer, you will reproduce more often than something that does not have that advantage, right? So if you're getting killed by the new predator, you're not going to be reproducing too much because you're dead. So essentially, that's what I'm trying to talk about in this answer. I feel like it was a little bit wordy, but here's the key here. The mutants survive better than the normal bunnies. You survive better. You have a better chance of reproducing. We know that DNA gets passed on from parents to offspring. So if you're surviving better, your DNA is getting passed on, right? So therefore, the mutation is going to show up more frequently because the mutants are surviving. Hopefully, I feel like I'm explaining that a little bit wonky, but hopefully that makes sense to you. But let me know if it doesn't in the comments below. All right, question 3. Invent a new type of mutation in a new environmental condition that might affect this population of animals. How might natural selection operate on a population with this new mutation, a new condition? How would the population change over time? That's a big question. Let's go back here. So, in other words, it wants us to create something new that we don't see here. So I want to see what hasn't been talked about. So restricted food, new predators, snow cover. Does it have a different one? No, new predator. Okay, so here's my initial thought was when I see forest and I think what could change. One environmental change that could happen would be a forest fire. A mutation that could happen would be, we're going to call it black fur. Okay, so I wonder, do you know where I'm going with this right now? So what's a forest fire going to do? And then is black fur going to be beneficial or not? So let's talk about what's going to happen. The forest fire would turn the forest environment darker and more black because of all the, how do I spell charring? I think that's charring. You know what I mean? Everything's burning, so it's going to be turning black. Bunnies with black fur. No, that's apparently not how you spell charring. 2 R's, I'm going to guess. Yeah. Bunnies with black fur, are they going to be doing better or worse than bunnies with brown fur? Will have an advantage because their black fur will blend in with the new darker surroundings. Okay, so what have I answered so far? I've answered a new mutation, a new environmental condition. I've talked about how natural selection, well, I haven't really talked about this yet. So I've really only covered this sentence. Now let's talk about what's natural selection going to do for this new mutation, new environmental condition. So black fur bunnies are going to have an advantage. So what's going to happen over time? Over time, black bunnies will survive at a higher rate because they blend in with their environment. So future generations will include more black bunnies and fewer brown, I'm going to call them regular fur bunnies. Okay, now have I answered everything? I've talked about natural selection is going to favor the black fur bunny, how the populations change over time. Future generations will include more black bunnies and fewer brown and regular. Okay, that's a pretty good answer. I really like this question because you can be pretty creative. You don't have to use the example. I'll be curious to read what you guys came up with because I think it's a pretty open-ended and cool question. So again, think of environmental change. Think of what could happen to the bunnies in terms of mutations. You don't have to stick with fur color. That's just what came to my mind right away. But anyway, I'll be curious to see what you guys come up with. All right, question 4, last one here, and then we will be all set with this lab. Scientists have discovered by looking at fossil records that the ancestors of giraffes had shorter necks than giraffes today, make a hypothesis about how long necks evolved in giraffes through the process of natural selection. This is one of my favorite questions because I think giraffes are cool. Also, if this quarantine stuff ever ends and you have a chance, if you go to the Columbus Zoo, I think you pay like $4 and you can feed the giraffes there. It was really, really cool. They tell you can't pet them, but you can pet them if you're really quick and no one's paying attention. But their tongues are like huge and purple, and they'll come grab the food out of your hands. It's really neat. So anyway, do that, but don't pet them. Don't do it. So let's talk about giraffes. How could they possibly get longer necks? Let's see. What does a longer neck do? Does it give you an advantage or is it a disadvantage? Let's think about this for a second. Why do giraffes have longer necks? What does it do for them? So I can picture now a giraffe eating off of the top of a tree and he's reaching food that no one else can reach. So that's giving me kind of a hint here. Let's talk about it. Giraffes with longer necks are able to reach food sources that other animals, including shorter neck giraffes. Excuse me. My dog's drinking out of the toilet. Daisy, stop drinking out of the toilet. You look guilty. She's got water dripping out of her mouth, and it's toilet water. How lovely. Okay, so giraffes with longer necks are able to reach food sources that other animals, including shorter neck giraffes, cannot reach. This means that over time, keep misspelling giraffes, giraffes with longer necks will have a better chance of survival because of their access. That is not how you spell survival. Whoop. There we go. Because of their access to more food. Let's see. Now, what's going to happen to the population? So this is kind of like the same question up here for question 3. How might natural selection operate on this population? And then how would the population change over time? Therefore, longer neck giraffes will reproduce more successfully, and the population will include more longer necks and fewer shorter necks over time. Let's double check our answer here. Giraffes with longer necks are able to reach food sources that other animals, including shorter necked giraffes, cannot reach. This means that over time, giraffes with longer necks will have a better chance of survival because of their access to more food. Therefore, longer necked giraffes will reproduce more successfully, and the population will include more longer necks and fewer shorter necks over time. And that's really all there is to it. Going back to Darwin, it's the same thing with the finches, right? They have the different beak sizes. Why would they have different beak sizes? Because that beak size gives them an advantage. If you have the advantage, you live longer than those without it. And then you can reproduce more successfully. So this is a really, really good. I know that the simulation is kind of lame and outdated, but the ideas that it presents are really good. I think it's a really strong way of looking at how populations can change over time. We'll do a little bit more with this. We're just getting started with natural selection. There's a lot of cool stuff to talk about in here. But hopefully this helped. I know a lot of people were confused about this lab. And I apologize, I can't be there to help you, but hopefully this helps. As always, let me know if it didn't, or if you need anything. Make sure you subscribe and like this video, or whatever YouTube people say. I'll talk to you guys later. See you tomorrow.